Welcome back to Robotics Mechatronics System Design. We will continue with the topic of pneumatic control valves. Um, on, on this slide, we discuss three-stage directional valves. So far, most valves that we had were um, basically those directional valves with uh, two basically positional stages. Okay, but now you could see that we have three squares, so it means that we could have three stage or we could have three possible positions. On this one, for example, um, the mid position is closed. Okay, so this is a new type of stage that we never had so far, and you see that all ports are closed. On this one, and this is a 3 by 3, so you have only 3 ports. This one is a 4 by 3, so we have 4 ports, and the mid position is also closed. This one is 5 by 3 wave valve, and the mid position is closed. This one is 4 by 3 valve, and the mid position working lines exhausted. So So you see that both of the working line, the port 2 and port 4. Okay, so let's say these two ports are connected to a double acting cylinder, and both of these ports now at this middle stage are connected to the atmosphere, and the pressure on both chambers are equal to the pressure in atmosphere. This one is a 5 by 3 wave valve, and on the mid position we have a pressurized, basically pressurized in mid position. So it means that both port 2 and port 4, both of them are pressurized and are connected to the compressor. So now if these two ports are connected to a double acting cylinder, both of the chambers are pressurized and they have a high pressure. And this one is a 4 by 3 way valve, and we have a pressurized in mid position. So these two are equivalent in terms of having a high pressure on port 2 and port 4. So now let's see how we could basically put these type of three-stage directional valves in application. On this homework 14, so you see that we have a cylinder here, and the cylinder from one side is connected to a fixed bar. From the other side, it is connected to a gate. Okay, so let's say this is a gate, and this link is connected to a gate or door that opens and closes an opening. So the mechanism in the figure opens and closes the material flow gate. So this is a gate that is opening the material flow gate. It could be a channel of water, or it could be a flow of, let's say, some type of, let's say, wheat. Okay. The gate should stay open in any possible position. Okay. So what does that mean? It means that, for example, the water flow should not open or close the gate itself, and the gate should stay firm at the specific position. The speed of the gate should be adjustable on any directions. For the convenience of the control signals, could be initiated from two different locations in the factory. Okay. I will go through the solution, but we should use a three-stage position directional valve as a main valve for this cylinder. And the reason is that since we want to keep the gate firm at any specific position, and we don't want the flow rate of the material changes the opening of the gate, it means that at basically the specific position or desired position, the pressure of the chambers, both chambers, left and right, in this cylinder should be high. Otherwise, the flow rate could affect the gate opening and could move the rod or the piston, because you have a low pressure on one side, and that will basically affect like a spring. Okay, so this is a solution. We are using 5x3 directional valve as a main valve, and since we want to basically operate it from two possible positions in the factory, we are using these OR valves. Okay, so we have these OR valves. One of these 3x2 directional valves are for opening, and the other one is for closing. And the other pairs are located on the different side of the factory. So how this main valve here, this three-stage position valve, is helping us to keep the gate firm at its location. So you see that on the middle stage, port 2 and port 4 are completely blocked. So it means that we have same pressure and high pressure on both sides of the piston. And these check valves are for adjusting the speed of the forward and backward motion. And remember how we should position them correctly. Otherwise, we cannot have basically highest possible power. Other pneumatic control valves, one of them is pneumatic timers. Although the application of these type of valves are dropping because of the PLCs, because in PLCs we could have timers, but still they are in use, and we could easily simulate them in Fluid Sim. Okay, so what we have here is power pneumatic timers. These are the industrial application of these type of timers, and you see that we have a knob here, or we have a knob that we could adjust the time delay. And here we have the symbol. In Fluid Sim, you could find the whole symbol as a group, and you could drag and drop it on to your simulation. Okay, so you could make it by your own, or you could just use the already group one and drag and drop it. So let's see what we have here. We have a 3x2 directional valve here. Okay, and we have the input port, or the main port, that is connected to the compressor. We have an output port, and we have exhaust port, which is connected to the atmosphere. Okay, so far we have just a normal a simple 3x2 directional valve, which is spring returned. Now here we have a check valve, and here we have a reservoir, okay, or like a tank. That tank or reservoir keeps the air inside and works like a capacitor in electrical circuits. So here we have a pilot port or the control signal port, and see how it works. So when the port 12 or the pilot port is pressurized, the pressure starts to increase in the capacitor or the reservoir, sorry, capacitor, reservoir. Okay, so the pneumatic reservoir here. Okay, so first the reservoir basically absorb the airflow, okay, until the pressure of the reservoir increases and reaches to the specific level. At that point, the airflow cannot be absorbed by the reservoir itself, and it has to go to the 3x2 directional valve. So that reservoir itself creates a time delay for activating that 3x2 directional valve. Now, after a specific time period, which is related to the capacity of the reservoir plus the airflow that could be adjusted in this check valve, the 3x2 valve will be activated, and the port 1 will be connected to the port 2, and the port 2 will be pressurized. Okay, so this is, let's say, on delay timer. It means that we have a delay between the time that we send a signal to the pilot port until the 3x2 directional valve will be activated and the port 2 will be pressurized. Okay, we have a homework here that we need to use one of those pneumatic timers. On this homework, we have an indirect control of double acting cylinder. So it's not new to you. You had indirect control of double acting cylinder before, and the speed could be adjustable for forward and backward motion. It means that you need to have check valves. Position control signal manual or pedal. So easy, you had this, and negative control signal automatic with specific delay. So this is where that you need to put one of those pneumatic timers. Let's jump to the solution. We have two possible solutions. I'm going to present to you these two possible solutions. The first one is very good for the educational purposes. You will learn how a pneumatic time delay works. So we have this double acting cylinder in direct control. We have a main valve, we have a secondary valves here, and for the forward motion we have either push button or the pedal. So we have an OR valve here, and for the automatic motion we have this 3x2 directional valve, and this valve will be activated once the rod reaches to the end of its stroke course. Okay, so A1 is the sensor here that activates this directional valve. Okay, but what happens when the A1 sends a signal and this valve is activated? So you see that now the port 2 will be pressurized, air passes through this check valve and goes to this single acting cylinder here. So this single acting cylinder here acts like a reservoir. Okay, so it does nothing except basically maintaining air inside its chamber. So now here we have basically a pressure gauge here. Okay, so all of this pressure gauge, all of these symbols easily could be found in Festo-Floyd sim. So you could put this pressure gauge and see how the pressure changes. You could set, for example, the pressure of these compressors to 6 bar, and you see that when you start the simulation, you see that when this valve is activated, it takes some time until this pressure gauge reaches to 5 or 6 bar, because air is basically absorbed by this single acting cylinder. So that creates a delay. When it reaches to 5-6 bar, then this directional valve will be activated, and the port 2 will be connected to the port 1 and will be pressurized, and the main valve will get the signal for the backward motion. Okay, so you see that we are not using a pneumatic control delay group, but we are using alternative components here. But you see that basically the functionality of this circuit is very similar to the pneumatic control delay valve. On this solution, for the same homework, we are using that pneumatic on-delay timer, and it works the same. You could double click on the group here on this pneumatic timer and change the opening and capacity of the reservoir and opening of the check valve, and you see that basically what you are doing, you are increasing or decreasing the delay or time delay. Another homework is indirect control of a 2 double acting cylinder, and by pressing start, cylinder 1 starts, and then with a delay the second one starts. Both of them should move slowly. By pressing stop, both should retract it at the same time and fast. So for the forward motion, we have a delay between the movement of the first cylinder and the second cylinder, but for the backward motion, both of them should be simultaneously, and they should retract at the same time. And you see that we have a different speed for the forward and backward motion. So you should use basically some sort of check valve or quick exhaust valves. Okay, so here is one possible solution. Again, pneumatic circuits sometimes don't have a unique solution, so you may come up with a different solution. If you do the simulation and it works according to the characteristics and details of the problem, so you have a basically right answer. So we have two cylinder, double acting cylinder, and you see that here for the forward motion we have this check valve, so we have a slow motion. For the backward motion we don't have check valve, so it should be quite fast. We could use a quick exhaust valves to have a faster backward speed. Okay, so now we have these two double acting cylinders here, and we have a start and stop button. Okay, so we have two main valves for each of these cylinders. Okay, so remember that when we have multiple cylinders, we should have one valve or one main valve dedicated for each of those cylinders. So you see that we have one main valve for this one and the other one for the other one. Okay, so these are the main valves. Now we have another 5x2 directional valve here, and you see that basically here for the port 2 is connected directly. Okay, so port 2 is connected directly to the right side of the main valves. Okay, so port 2 here, if we follow it, it goes to the right side of the main valve for the cylinder 2 and right side of the main valve for the cylinder 1. So we don't have any delay once we press the start. Okay, but what if we press the stop button? Okay, so then port 4 will be activated, and port 4, you see that it's connected to the pilot port of the time delay timer. It also provides air to the main port of the timer, which is port 1, but port 2 won't be activated until it gets the signal from the port 12 or the pilot port, which happens with a delay. So once the port 2 here of the timer will be activated or pressurized, then it could activate main cylinders of both, for one of them, for it could activate or pressurize the main directional valve for the cylinder 2, but not for the 1, because for the 1 is connected directly, because we wanted to have a delay between movement of the cylinder 2 and cylinder 1. So for the forward motion, now we have a delay. For the backward motion, we don't have any delay because it doesn't go through the undelayed timer. So you see that the circuit now, it's a bit complicated, but once you make it by yourself and start simulating, you see that you could easily identify and diagnose the issues in your circuit and make it complete as it's desired. Another homework on this one, we want to analyze the following pneumatic circuit. So we want to explain how this pneumatic circuit is going to work. What I suggest you to do is to make this circuit in Festo-Floyd sim. But before that, this is somehow a reverse problem from what we had so far. So far we had the problem that we wanted to design a circuit, but now we want to understand how the circuit works. We have the circuit already. So try to analyze it by yourself before doing the simulation, but then at the end do the simulation in Festo-Floyd sim and check your answer and see if you have understood basically the question properly. Okay, so we have a main valve here for this cylinder, and we have a quick exhaust valve here, so it will be retracted quite fast. And here we have a timer we have a timer, and the pilot light, pilot line is connected to the port 2. Okay, so this is a pilot line here is connected to the port 2. Okay, so let's see what happens here. For the backward motion, okay. Yeah, so okay, so for the forward motion, okay, so for the forward motion, yeah, okay, so yeah, so let's go for the backward motion because this is exactly the status of the system right now. So for the backward motion, you see that the port 1 for the main valve is connected to the port 2, and the air will be exhausted fast and quick from this port. And you see we don't have any delay. We don't have any delay for the backward motion, but for the forward motion we have a delay. And that delay happens when we press this pedal here. So once we press this pedal here, basically we need to have change in the status of this directional valve, and that happens with the time delay. And with the time delay, we could then changes the status of the main valve. So so if I want to say briefly, what is this circuit? We have forward motion with the time delay, and we have a quick backward motion without any delay. Okay, so now the previous pneumatic timer that we discussed so far was a power pneumatic timer or on-delay timer, and this one we are going to discuss here is an exhaust pneumatic timer, and it's basically off-delay timer. You see that it's very similar to the previous one, the structure. However, the initial position of this 3x2 valve here was different in a power pneumatic timer. So you see that in a normal condition, one is connected to 2 and is already power, but once we send the signal to the pilot line or port here, it takes a while until it changes the status or basically exhausts the air or connects the port 2 to the port 3 or the atmosphere. So we have a delay for turning off this directional valve. So that's why I like to call it off delay timer, which is similar to the PLC terminologies that we will go through that later in this course. Or as it is clear from the name is the exhaust pneumatic timer, it means that the port 2 will be connected to the port 3 or atmosphere. Okay. Now let's go through one example. We want to have indirect control of double acting cylinder, and the speed of forward motion is fast and backward motion is extremely fast. So when we say extremely fast, it means that we should use one of those quick exhaust valves. Positive control signal, pressing the manual button. Negative control signal, the rod must be retracted after a specific delay time. Okay, and on this one, you could implement it with a power time delay, but we want to basically implement it with exhaust time delay. Okay, so here is one possible solution using a off delay timer or exhaust time delay. As you could see that the forward motion is fast and the backward motion is extremely fast because of this a quick exhaust valve, and we have one of those off delay timers. Example 9, indirect control of double acting cylinder for washing parts machine. The speed of forward and backward motions are adjustable, manual mode. Both motions are manual by manual button. This is a manual mode. So we have a two mode here and we need to switch between two mode. One mode is manual, the other one is automatic. On the automatic one, both motion on preset times. Operation could be stopped anytime by a stop button. So this is a washing machine, so we need to have a preset time. Okay, so for let's say a specific amount of time, those parts should be washed, or the timer should be start with some delay and should be stopped with some delay. Okay, we have the manual mode. We have this manual and this stop start, or I call it manual because we also have a start button that starts the whole system. And if you have an automatic mode and we are using these OR valves, we have a main valve, we have double acting cylinder, two sensors A and B that activates these two valves, and we have a timer here. Okay, the timer only works in the automatic one, not the manual one, as basically was explained in the description of the example 9. And we have a start button that starts and stops the whole system, and we have a choice to start or stop the cylinder manually, or leave it to be operated by the automatic mode or these sensors. Okay, another topic is numbering the pneumatic circuits. So you see that the pneumatic circuits could become complicated by increasing number of cylinders and valves, and we need to have a unique numbering system to identify cylinder sensors, valves, and understand the relation between them. Okay, so we need to follow a specific standard to first understand and develop our circuit, so others could also understand the relation between parts and interpret our circuit easier. The numbering starts from main line to derivative lines or branches. So main line comes from the main compressor, and then there will be some derivatives or branches. Air preparation line parts start with 0. Okay. And when it comes to the air preparation parts, I will explain what I mean by those parts. Okay. Then we have a pilot ports and lines get the second digit like 2, 1, okay, 2, 2, and etc. We have actuators get the alphabet A, okay. A stands for actuator. Directional and control valves get the alphabet V. valves. Sensors get the alphabet B. Switches get the alphabet S. And solenoids get the alphabet M. Okay, so here is one example, example 10. This is a pneumatic circuit of handling station in MPS 500. If you review handling station, watch the video, you will see that we have three pneumatic actuators. One is for the vertical motion, or basically the vertical motion of the crane, or the handling handling system. Horizontal. The other one is for the vertical motion, basically that arm that extends to reach the part and grab the part, and then the last one is for the gripper that opens and closes and basically grabs the part. So we have three actuators. Okay, so you see that we call it 1A1. So the first one, because it's the first branch. Okay, so you see that this is the air preparation line. Okay, so this is the air preparation line, or comes from the air preparation line. We don't have an air preparation line itself here in this pneumatic circuit. It's not shown, that's why it doesn't start with 0. Okay, so it comes from the air preparation line. This is the main branch, and then we have 3 branches. First branch starts with 1, the second 2, and then the third one starts with 3. And you see that we have 1 at the beginning of each of these, the symbol of each parts. Okay, so the first one we have 1. A is actuator 1. So we have only one actuator in this branch, so that's why we have A1. If we had a second actuator also in this branch, then we should call it 1A2, but we don't have it here. So also here on branch 2, we have an actuator. First actuator on this branch is 2A1, and here we have 3A1. Now, on this cylinder, we have 3 sensors, one at the beginning, one at the middle, and one at the end. And you see that this is a rodless cylinder and is magnetically coupled with the carriage. So we have sensor B, okay, so it should start with B on this branch, 1B1, 1B2 second sensor, 1B3 is the third sensor. Now here we have valves. We have 2 check valves on branch 1. We have a second valve and the third valve. Let's see what is the first valve. The first valve is 1V1, and it's grouped together. Okay, this is a group valve. Okay, it's basically a little bit advanced valve. The reason all is grouped together because physically in a real system, all of them coming as a group. Okay, so it's designed as a integrated valve. Okay, so this is an integrated valve with all of these components all together. That's why it's grouped here in this circuit, and they call it 1V1. And this is the main valve. This is the main valve. This 1V1 is the main valve for this cylinder. So here we have 2 pilot non-return valves, and you see that the pilot lines starts with 2 digits. So we have 2121 pilot lines. So here we have a solenoids. The first solenoid on the first branch is 1M1 and the second one is 1M2. We have lots of pilot lines here, like these 14 and 10 or 112 and 110. These are, many of them are internal, some of them are external, like these 12 and 14 here. It's a very, it's a bit advanced valve. We could simulate it with easier or basically simpler components. We don't have it as a group. We could use each of these 3x2 valves and non-return valves to simulate it exactly how the way it works. On the second line, I explained the actuator. Now we have a second valve, which is V2 and V3. What is the main valve for this cylinder is 2V1. Okay, so this is 2V1, this is a valve, and we have only one solenoid, which is M1 on this branch. And similar here, we have only one valve, which is the main valve for this cylinder, and that one is valve 3V1, and we have only one solenoid 3M1. So you see that with that numbering system, we could easier understand and identify the relation between parts, between valves and actuators and solenoids and actuators and sensors and actuators and so on and so forth. Okay, see that, for example, here all of these valves are grouped together and they call it 0V1. The reason is that it starts with 0 because it's connected directly to the compressor, plus it's not dedicated specifically to specific branch or actuator. And again, the reason they are grouped here together because on a real system, all of these valves are grouped and are integrated into one valve. But you could basically simulate it again in Fluid Sim. You don't have to group it. Grouping in Fluid Sim is not that difficult. You will choose multiple parts and you will group them together and name it. So these basically dotted lines don't have any effects on the functionality of the circuit. It just shows us that on a physical system, which components are grouped together or which components are coming together as an integrated part. Okay, so we are almost done with the control valves, or I could say all pneumatic valves. Now I'm going to briefly explain control systems. So far, we didn't have PLC in our circuit. We only had, let's say, a cylinder and a directional valve and some control valves, but we didn't have any PLC. Now, we could start to have PLC by getting feedback from the sensors. So sensor information will go to the PLC. PLC will do some processing. There will be some codes on the PLC, sequences in the PLC, and based on the sequences, we will send output to our valve. So let's say we could have an on-delay timer inside the PLC, and we could basically don't use those pneumatic timers, we could replace it with the PLC, and then we will send a signal, let's say with the delay, to the directional valve. So you see that the logic part of the system uh, could be inside the PLC. The PLC accepts some inputs, and then it has some outputs, and it goes, for example, to the solenoid of these directional valves. So you see that we have a feedback system here. Let's recap what we have studied. So on valves, we studied directional valves. On valves, we studied the control and the logical valves. Methods of actuation and activation, mechanical, pilot, pneumatic. Pneumatic symbols, ISO standard characteristics, read and interpret. Simulate and draw a pneumatic circuit, closed loop and open loop. And we understood through examples and homeworks what's the meaning of bistable and monostable valve. So we are at the end of valve session, and please submit all homeworks on valve slides, both part 1 and part 2 to Moodle.